There is a machine on Earth that has to be cooled to almost absolute zero, colder than outer space itself. Not to protect the machine, but because even the smallest disturbance from the outside world can destroy the fragile information it is trying to control. Can you guess what kind of machine this is? This is a quantum computer, one of the most ambitious technologies humans have ever created. But the strange thing is, its power does not come from simply being faster than a normal computer. It comes from using some of the most unusual rules of the quantum world. To understand why this matters, we first need to look at the computers we use every day. From smartphones and laptops to massive data centers and artificial intelligence systems, every classical computer is built around a basic unit of information called a bit. A bit works like a tiny switch. It can only exist in one of two states, 0 or 1. Billions of transistors inside modern processors constantly switch between these states, creating the entire digital world we rely on today. But when humans move far beyond normal scales, down to the level of atoms and quantum particles, the familiar rules of our world begin to change. Nature no longer behaves the way we experience it every day, and quantum computers are designed to take advantage of these strange physical laws. Instead of ordinary bits, quantum computers use qubits. A qubit can exist in a combination of multiple possibilities before it is measured. This phenomenon is called quantum superposition, but it is also one of the most misunderstood ideas in modern technology. A quantum computer does not simply test every possible answer at the same time like a magical machine. The reality is much more complex. Quantum algorithms use superposition, quantum interference, and probability to control how information evolves during a calculation. They increase the chance of measuring the correct answer and reduce the probability of incorrect outcomes. This is not just a faster version of traditional computing. It is an entirely different way of processing information, a new approach built around the rules that control the smallest parts of our universe. So why do humans need a completely new type of computer? Because there are problems where even the most powerful supercomputers begin to reach their limits. One of the most important examples is simulating nature at the atomic level. The molecules around us are controlled by quantum mechanics. Every chemical bond, material property, and molecular interaction follows quantum rules. But when a system contains many interacting particles, the number of possible states grows incredibly fast. Some calculations become too large for traditional computers to handle efficiently. Quantum computers may be able to approach these problems in a more natural way, because they use quantum systems to study other quantum systems. This could help scientists discover new medicines, understand how proteins and molecules behave, and design materials that have never existed before. Future quantum computers could help create better batteries, develop more efficient chemical processes, improve complex optimization problems in science and industry. But before this future becomes possible, engineers have to overcome one of the hardest challenges in modern technology. Qubits are extremely fragile. A tiny amount of energy from the surrounding environment can destroy their quantum state. Heat, vibration, electromagnetic noise. All of these can cause quantum information to disappear. This problem is known as quantum decoherence. That is why a quantum computer looks unlike any computer most people have ever seen. Inside advanced laboratories are enormous systems built for one purpose: protecting a tiny quantum chip from the outside world. The most recognizable part is the dilution refrigerator, the giant golden structure often shown in pictures of quantum computers. But surprisingly, that is not the actual quantum processor. Most of this huge machine is a cooling, shielding, and signal delivery system designed to protect the real computer inside. Each metallic stage lowers the temperature step by step. Special cryogenic wiring carries control signals from the normal world above, down into the extreme environment where quantum information can survive. At the lowest stage, the temperature reaches only a few thousandths of a degree above absolute zero, and hidden there is the true heart of the machine, a small quantum processor containing the qubits. a chip much smaller than the massive system protecting it. This tiny device is where quantum information is created, controlled, and measured. But even after reaching this level of engineering, quantum computers are still developing technology. Today's qubits are not perfect. They can make errors during calculations. And building truly powerful quantum machines requires solving the problem of quantum error correction. Scientists may need many physical qubits working together to create one stable, logical qubit. This is one of the biggest challenges standing between today's experimental machines and the large-scale quantum computers researchers hope to build in the future. So quantum computers are not designed to replace your laptop. They will not simply make apps open faster. They will not make every video game run better. And not every problem needs quantum computing. They are built for a different purpose. Quantum computers are designed for special challenges. Problems where traditional approaches may take an almost unimaginable amount of time. A giant machine, built to protect some of the smallest and most fragile phenomena in nature, and perhaps in the future, the coldest computers on Earth will help humans explore some of the deepest mysteries of the universe. Not by calculating like ordinary machines, but by speaking the same language as nature itself.